Okay, so I think now this is going to work properly. All right, finally. So we had some issues with the recording in the first class, so I'm just going to re-go through the class notes very quick. So dynamics, we gave a basic definition for dynamics to be the study of motion. There are two different ways to study dynamics. So the motion of an object, either just by kinematics, meaning that we just be using the equations of A equals dv dt or V equals ds dt, okay, where A is the actuation, V the velocity, T is the time, and S is the position. Or we can use kinetics, which this time we use Newton's second law. So basically, if you know the forces and the mass of a rigid body, you can determine what will be the actuation. And then once you know the actuation, you can come to this equation, integrate to find the velocity. Once you know the velocity, you can come to this equation again, integrate, and find the position, okay? So the motion of any object, you can always break it into two parts. The object can only be moving in translation, meaning that then this term will be zero, or if the object is only moving in rotation, then this term will be zero, but the object might be moving in a combination of translation and rotation, and then you will have then terms that are related to the translation and some terms that will be related to the rotation, okay? And that's important later on when we start deriving the equations. So this is a quick review, something you should have done in physics. But basically, I just go through the procedure that we'll be using later on in different cases for the actuation not being constant, but we start by A equal to constant. So the first thing to do is write down the equation. And then here we separate the variables. You see, we move dt to this side. Here we have V, so we separate the variables from this step to this step. Now that you separate the variables, you can integrate. We integrate and we solve for the final velocity. This will be the expression of the final velocity. Now using the second kinematic equation, V equals ds dt, we separate the variables again, V equals v dt equals ds. Here, remember that V is given by the expression we derived before. We substitute over here, but again, we separate the variables. You see it's t and t. We separate the variables, now we can integrate. We integrate and we get to the expression for the position that you should have seen before. Now this is another equation maybe that you might remember, but this one you see is only related in velocity, acceleration, and position. So there is no variable of time. So there are two different ways to, if you want to eliminate the variable of times. The more mathematical is what is known as the chain rule. So basically we have A equals dv dt. We write dv divided by ds because we need to introduce the variable s times ds over dt, but we know that ds over dt is velocity, okay? So now we just rewrite A equals v dv ds. We do separation of variables, A ds because A constant equal v dv. We integrate, we do some basic algebra, and we get the expression for the final velocity to be the initial velocity squared plus 2 times A s final minus s initial. Okay, the other way to get to this expression here, or this one, is to write down the two kinematic equation, recognize that we want to eliminate the variable of time because it's not in this equation. So we write these two equations, eliminated, but in dt equal to dv over A equal ds over v. We look at these two terms. We rearrange them. If you see A ds v dv, and basically it's the same thing that we have over here, or just to show that we can get the same, I can write it under this one. Okay, here's exactly the same procedure again for the rotation, but again, you see, first step, write down the kinematic equation. 2, separation of variables. Okay. 3, integrate. 4, we solve for whatever we need. And here we do the same thing. Chain rule again for the angular acceleration would be the same thing, but we use here omega, which is the angular velocity. Theta is the angle, okay, of the formation, and we get a similar expression. So all this we did to show you that we always get to the result if we follow the following procedure. Write kinematic equation, separate the variables, integrate, and then solve. So the first case we're going to do, and actually is the most complicated, we're going to look at this time the actuation in function of position. It's not to consider the actuation constant is good in some cases, but it's not good in every single case. So for example, let's say if let's say you are driving on a road and then the road becomes a dirt road, you will see that if you don't make any change on the on your speed, if you want, once the actuation is not going to be the same once you go on the concrete or once you go into the dirt road. Okay, all right. And for example, you could also have, let's say, when you start driving faster on the highway, the faster you go, if you want, the higher the resistance of the wind on your windshield. So in that case, you see that the acceleration can also be in function of the velocity, or let's say the acceleration can be in function of time. Okay, let's say you decide to change the acceleration in time, so it's not all the time constant. You can, let's say, press more or less on the actuator in function of time. So this time the acceleration will not be constant, again, will be a function of time. So in this case, in function of position, this is the mathematical way to write down A in function of position S. So we follow the procedure. One, kinematic equation, A equal dVdt. In our case, A is in function of position, equal dVdt. Second step, separation of variables. Okay, the problem here, you see we have S, V, and T. So we need to eliminate that T over here, get rid of that T. So if we use the chain rule, we have A of S equal dV ds, ds dt. We know that ds dt is velocity. So A of S equal V dV divided by ds. We separate the variables. We put on the left-hand side all the variables in function of S, A S ds. And on the right-hand side, all the variables in function of V dV. Now that we have separated the variables, we can go ahead and integrate, and then we'll solve for whatever is needed. So in this case, let's look at this problem, 13.55. This is some type of bullet that is in a cannon, okay? And they give us that the acceleration is in function of the position. That's what we know, and it's given us A equals C over S. The initial position is 1.5 meters, final position 3 meters, initial velocity 0, final velocity 200. So again, okay, even if we don't know anything, let's just follow the procedure and see what happens. So write down, first step, write down kinematic equation, A equal dVdt. A is C over S, equal dVdt. Again, we use the chain rule, dV ds, ds dt. So this is equal to C over S equal V ds. Now we only have two variables, V and ds. We can separate the variables. We put on this side C ds over S equal V dV, separation of variables. Now that we have separated the variables, we can go ahead and integrate. So we integrate between the initial position, final position, initial position, final position. So the integration of ds over S is the log of S, all right? The V dV will be V squared over 2, and then we have 1/2 V final square minus V initial square. Doing just some basic algebra, or we have this, but we know by using this expression, log of A over B is equal to log of A minus log of B. So you can solve for C either under this form or this form. Both of them will yield to the same result. Or we solve for whatever we need. So we do the numerical substitution. I substitute here just the values, and we get that C equal to 28.85. And with this, we did finish the class that saying that the next example we're going to be doing is the acceleration in function of time, but again, it's the same procedure. Write down kinematic equation. All right, this time A of t is in function of t, so it's the only two variables, t and v. Separation of variables, at dt, dv, okay, function of t. Now that the variables are separated, we can integrate, and then we will solve for whatever we need. So in the next class, we're going to be solving another problem similarly to this one. All right.